In this lecture onwards, let us discuss the FIR filter design. So till now we have discussed the methods of how to design an IIR filter, right? So you can do the IIR design very confidently. Why? Because your base was analytical base. So we started with the analytical equation, right? So from that, we got the IIR filter. So everything was obtained in a closed form, but that is not the case in FIR. So FIR, unfortunately, is not so. In FIR, there is a lot of uncertainty. And in every step you have to ask yourself, am I proceeding in the correct manner? Will this satisfy the specs? Right? So in FIR you start almost blindly. You see in IIR, infinite impulse response filters, there were analytical formulas for calculating the Butterworth order NB and the Chebyshev order NC. Right? To calculate these orders, we had analytical formula, if you recall. But there is nothing like this in FIR. So FIR, no such formulas. So everything goes by trial and error method. Okay. So in FIR, you only have empirical formulas. So in IIR we had an analytical formula, and here we use empirical formulas. And these empirical formulas sometimes work and sometimes may not work. So we need to be little careful. If the empirical formula gives you an order of, let's say 17, you might have to use an order of 20 or 21. So like that. So empirical formulas always have this kind of tolerances, that is uncertainty. Even then you can ask a question, why should we use FIR? If the filter design is so uncertain that at every step you have to go back and ask yourself, am I proceeding in the correct direction? Have I taken the correct order? Have I taken the correct procedure? If that is so, then why should you use FIR filter at all? So the answer is this. The first reason is the FIR filter is unconditionally stable. That is the first reason. This is one reason. And the main reason is, the very important reason is linear phase. So this is a very, very important, key important factor. Because of this only we are discussing this FIR filter. Okay. So linear phase is of the utmost importance. If linear phase is strict requirement, for example in data transmission or data processing, if a rectangular pulse you transmit and this rectangular pulse becomes smeared, it may be like this, because of the delay distortion. This happens because of something called a delay distortion. Then rectangular pulse does not convey what you wish to convey. Similarly, you may have speech processing. So there also we need a FIR filter. So in speech processing, linear phase is a strict requirement. So you have to use FIR filters. Okay. So there are two main reasons. One is that it is a linear phase. This is one advantage. And the other is that it is unconditionally stable. There is a third advantage. You see, if you have a non-causal FIR filter, then you can make it causal. How? By simply shifting the whole thing to the right. Isn't that right? That is, you multiply the required number of delays. So, realizability is not a problem. Not a problem in FIR filters. So, realizability of an FIR filter is not a problem, although it is not a great disadvantage. This is not a great advantage, but since you are listing advantages, this is one of the advantages. And the disadvantage is that you have to use for this same specs a larger order. Okay, it needs larger order FIR filters. I mean, what can be done by a second order IIR filter may require a 20th order FIR filter, or it may require a 30th order FIR filter. So if you use higher order filters, then what happens? The cost will go up. So that is one disadvantage. Okay, larger order, and because of the larger order, cost also increased. And the second disadvantage is that the implementation, I mean, if you implemented by convolution in the time domain, it is very slow, because implementation is slow. If you implement, it's a slower speed, okay, because the implementation uses convolution, and the convolution is a slow process. If you write a software or do the required hardware, this convolution involves multiplication and addition, right? So it is a slow process. Nevertheless, this is not a disadvantage. Why? Even though the convolution is a slow process, it is not a disadvantage. Why? Because convolution can always be calculated by DFT. See, in the time domain this is convolution, but the moment you convert to frequency domain, it will be multiplication, simply multiplication. So you take DFT and multiply, and then again take IDFT, inverse discrete Fourier transform. Right? So you have a system, impulse response h of n, and the input is x of n, output is y of n. What is y of n? Y of n is equal to h of n convolved with the x of n. So if you want to convolve x of n and h of n, you take DFT of h of n and DFT of x of n. You will get h of k and here x of k. Then multiply these two guys and then take IDFT. Okay, take the inverse discrete Fourier transform. And also this DFT is also a slow process. This is not a fast process. So to overcome that, generally people will use FFT, fast Fourier transform algorithm. And then instead of IDFT, you use inverse fast Fourier transform. That is why this FFT is popular, so popular. So FIR, finite impulse response filter, the disadvantage of slowness or speed of processing being very slow can be overcome by using FFT and IFFT algorithm. These design methods are something called semi-analytical methods. So the FIR filter is designed using a method called semi-analytical methods. It is not analytical method, it is semi-analytical method. On the other hand, IIR filter, if you take, where we used analytical methods, but here we use the design procedure called semi-analytical methods. There are only two of them in semi-analytical, because it is not exact like IIR. You cannot save it, or you cannot say it degree of confidence. that what I have designed is the most correct one. You can't say with full confidence. With certain level of confidence only you can say it. So there are two semi-analytical methods. One is called there are two semi-analytical methods. The first one is called windowing. Other is frequency sampling. And then of course you have the computer aided design. So that is called CAD method, computer aided design procedure, using something called REMIZ algorithm, exchange algorithm, REMEZ, REMIZ exchange algorithm. So REMIZ function implements the REMIZ exchange algorithm for FIR filter design. Okay, so using this computer aided design procedure, this REMIZ exchange algorithm is implemented. So what you do is, in this method, minimize the maximum error. Okay, so this is also called min-max method. What does it min-max? Min-max means minimize the maximum error. So the ultimate goal is you have to minimize the error, that's all. That is why this is called min-max method. So standard programs are available, they are very costly, and this method is a costly one. Okay, so they are very costly programs for design of an FIR filters using computer aided design, and such designs are called min-max designs, because these designs minimizes the maximum error. Okay, minimizes the maximum error. So they are called optimal in that sense. We will concentrate on semi-analytical designs, especially windowing method and frequency sampling method. Okay, often before you go to this CAD, one uses windowing or frequency sampling method to get a rough design. Okay, using this you design the filter roughly, you get a rough design, and then you polish this design with the help of computer aided design. You polish this result with the help of CAD. Now the philosophies that are used is extremely simple in windowing. For example, you have been given a desired transfer function. So we are discussing in the discrete time domain. So h of n, if you take Fourier transform dt of t, you will get h of e to the j omega. Now let me put a subscript here d. This d indicates desired. Desired means what I wanted. Desired transfer function. And you know the transfer function is periodic. See, even though this h of n is aperiodic, the moment you take Ct of t, continuous time Fourier transform, recall the properties of this transform. This h of e to the j omega will be periodic with period 2 pi. Okay, so with a period of 2 pi, and any periodic function, we know that any periodic function can be expanded in Fourier series. Please recall these things from your signals and systems course. So originally h of n is aperiodic. The moment you take Fourier transform, you will get transfer function, and that transfer function is periodic. And once it is periodic, we know that any function which is periodic with a period of 2 pi, that can be expanded in Fourier series. So what you do is expand this hd of e to the j omega into Fourier series. So this is going to be hd of n e to the minus j n omega summation n equal to minus infinity to plus infinity. So there are some coefficients, this one, and if you substitute n equal to 1, that gives fundamental component, and this is called a Fourier series coefficients. And in general you have to go from minus infinity to plus infinity. So this is the Fourier series expansion. Okay, which is the same as dTFT of this sequence h of n. So therefore Fourier series expansion of h suffix d of e to the j omega is the same as discrete time Fourier transform of hd of n. And therefore what is hd of n? hd of n is the impulse response sequence. Impulse response sequence. Agreed? So given a desired transfer function, h suffix d of n will be infinite length in general. The length will be infinite. So what you do is you first expand in Fourier series, and then you argue that this is IIR filter. Why is it IIR? Because the impulse response length is infinity. If the length is infinity, then you call it infinite impulse response filter. But what we want is finite impulse response filter. Okay, so because hd of n is of infinite length, and arbitrarily this is where the uncertainty comes. So what you do is you truncate it. Arbitrarily you truncate it. You truncate maybe at n equal to minus n1 some number to n equal to plus n1. See, the impulse response sequence extends from minus infinity to plus infinity. The 0 is somewhere here. So you truncate from minus n1 to plus n1 within this interval, and remaining sequence you discard, don't consider. Then the resulting sequence will define a finite impulse response. Originally the length is infinite, therefore you got IIR filter, infinite impulse response filter. Now what you have done is you truncated in the length of minus n1 to plus n1. So total length is 2n1 plus 1. Or let me say this is n, simply n, so that 2n plus 1. Now this filter is obviously not realizable. Why? See, the filter sequence exists from minus n to plus n, your h of n, and this type of filter is not realizable. You can't realize physically. Why? Why is that so? Why can't we realize it? Because this is non-causal. Okay, the impulse response is not 0 for h of n, is non-zero for n less than 0. So it is non-causal. So whenever it is non-causal, you cannot realize physically. So what is the solution for this? The solution is very simple. You simply multiply the whole thing by z to the minus capital N. Agreed? Simply multiply the resulting transfer function by z to the minus n. If you do that, then it will become a causal function, and then you can realize this. So once you multiply by z to the minus n, there is, it's easy to realize it. Now even if you do this, Okay, so originally the sequence length is minus infinity to plus infinity. You truncate it between minus n to plus n, and then since it is non-causal, you multiplied by z to the minus n minus capital N, so let it small z to the minus n, and then also there is no guarantee that you have satisfied the given specifications. Okay, and one more thing is this minus n and plus n is purely arbitrary. This minus n1 is purely arbitrary, and this plus n also purely arbitrary. Okay, so it's purely arbitrary to start with. You just start with some value, and then by trial and error method you can increase it. So there are empirical formulas to get you an idea of the order that you will require. So there are certain empirical formulas are available. You can use any one of them and you can estimate the rough order. But we can't assure you that is the exact order value. With that you can't proceed the designing. So what we will do is, instead of truncating, we are truncating from minus n to plus n. So instead of truncating from minus n to plus n, we will truncate from 0 to some capital n minus 1. Why? Because if you truncate 0 to n minus 1, there is no question of non-causality. Okay, so instead of truncating from minus n to plus 1, let us truncate 0 to n minus 1. So what is the length now? The length is capital N. That is, what we will do is, we will take h of e to the j omega, which will be on an approximation to the desired frequency response. See, the desired frequency response has the length of infinity, right? It extends from minus infinity to plus infinity, but we are truncating the desired frequency response like this. I'm sorry, I beg your pardon, not like that. I beg your pardon. So what we will do is, we will take an h of e to the j omega, this guy, h of e to the j omega, which will be an approximation to hd of e to the j omega. Now let us see what this hd of e to the j omega will be. And then this you can write the formula. This is the Fourier transform of continuous time Fourier transform of hd of an impulse response. So we will write this hd of e to the j omega as the summation hd of n e to the minus j n omega, n equal to n equal to 0 to, because we are considering now 0 to n minus 1, right, in this length, right? So that's why n equal to 0 to capital N minus 1. So the length is what? Capital N. So here we will take the summation from n equal to 0 to capital N minus 1, so that the length is capital N, and we have thrown out all others. So minus infinity to 0 thrown out, discarded, and similarly n minus 1 to infinity, that also thrown out. So I want a realizable filter. So h of z will be simply equal to hd of n z to the minus n summation n equal to 0 to n minus 1. Just I am taking the z transform. So here also I have taken length equal to capital N. So it is a finite impulse response sequence. Okay, so we do not know beforehand what this n should be. We don't know what this n should be. this capital N should be. So it is a guess. Okay, so N is generally obtained by guessing. So it is a guesswork. Fortunately for low pass filters, well, for any kind of filter, these people know at Bell Laboratories, at Bell Labs, including Kaiser, Rebiner and Gold and so on, they investigated a very large number of filters on the computer and they made the designs. They came up with some simple empirical formulas for estimating the order. So these guys came up with some empirical formulas at Bell Labs. Okay, so and this empirical formulas uses the specifications like the delta P and delta S, pass band tolerance and stop band tolerance. So given the tolerances in the pass band and stop band, there are some simple formulas for estimating the order. And now there are some complicated formulas also. If they require stiff, then there are some elaborate formulas also. If you need some, your requirement is very stringent, very stiff, then you have to use some complicated formulas. Otherwise you can use some simple empirical formulas. There are many. So it's not like IR filter. Okay, you have only one formula, you have to stick onto that and use it like that. No, not like that. Okay, so we will come back to these formulas a little later, but these formulas were worked out not with the kind of tolerance scheme that we are following. What do we follow? If we take a filter, the highest value is 1 and this is delta P and this one is delta S, right? In the pass band the lowest is delta P and in the stop band the highest is delta S. This is stop band, omega S and omega P, like this. But these people at Bell Labs, they have used some different notations. So what they used is, this point is, they said 1 plus delta 1 and this they said 1 minus delta 1 and this value is delta 2. Just notations are different, that's all. For some historical reasons, I don't know why they used it like this. So these empirical formulas that are given for a typical low pass filter, they use maximum as 1 plus delta 1 and the minimum as 1 minus delta 1. And in the stop band, the maximum value is delta 2. The empirical formulas are in terms of delta 1 and delta 2. But converting from here to our specs, what is our specs? Delta P and delta S. That is, we take this 1 as 1 plus delta 1 and this 1 minus delta 1 as delta P and this delta 2 as delta S. So converting from one spec to another is not a problem. It's a very simple process. Okay, so it won't need much effort. So these people at Bell Labs, they used these notations. So the empirical formulas that they derived uses these notations, delta 1 and delta 2. But till now, whatever we have studied, we used this delta P, delta S, omega P and omega S. Therefore, we need to know how to go from delta P, delta S to delta 1, delta 2, or from delta 1, delta 2 to delta P to delta S. So one should know how to convert the specs, convert from one notation to another notation. Okay, so converting from one spec to another is not a problem. All you have to do is, this is maximum value is 1 plus delta 1. So let us normalize this maximum value 1 plus delta 1, normalize. How do you normalize? By dividing 1 plus delta 1. So the maximum value will be 1. And what is the next value? Next value is 1 minus delta 1. Again divide by the same value 1 plus delta 1. So this is going to be, as per our spec, delta P. That's it. And then this value also, so this is delta S, sorry, delta 2, again divided delta 2 by the same denominator 1 plus delta 1. So this is as per our notation delta S. So I have two equations. 1 minus delta 1 divided by 1 plus delta 1 is equal to delta P. And if you solve this by componendo and dividendo method, you will get delta P is equal to 1 minus delta P divided by 1 plus delta P. Delta. I'm sorry. I beg your pardon. This is delta 1. So 1 minus, if you rearrange this equation, then you'll get this 1 minus delta P divided by 1 plus delta P. And delta S is equal to this one. Delta S is equal to delta 2 divided by 1 plus delta 1. So delta 2 also you have to express in terms of delta 1 and wait a minute, hold on. Yeah, we need to eliminate delta 1 and 1 plus delta 1 from. So we need to write delta 1 in terms of delta P and delta S. So how can I do that? So both sides you add 1. So which equation should I take? Okay. What is delta 1? Where is the equation? I'm sorry. Take this equation. Delta 1 is equal to 1 minus delta P divided by 1 plus delta P. You add 1 on the left hand side and the right hand side also you add 1. Then 1 plus delta 1 is equal to, take LCM, 1 plus delta P plus 1 minus delta P divided by 1 plus delta P. Then this delta P will get cancelled. So this is 2 divided by 1 plus delta P is equal to 1 plus delta 1, isn't it? Now substitute 1 plus delta 1 in this equation here. So delta S is equal to delta 2 divided by 2 by 1 plus delta P. So rearrange this. Delta 2 is equal to 2 times delta S divided by 1 plus delta P. That's it. So delta 2 I got. Delta 2 is 2 times delta S divided by 1 plus delta P. And then delta P, where is it? Delta 1. Yeah, let's say this is equation number 1. Delta 1 and delta 2 I got it. Okay, so I want to point out right here that those formulas for estimation, okay, this formulas 1 and 2, because they are the only things that are available. So you are in a ocean and you clutch anything, okay, clutch anything for support. So this is the only support, okay, this formula 1 and 2 that is available, and it required many hours of work on the computer by Bell Labs people to be able to come to this kind of formula. It is the only thing that is available. So between these formulas 1 and 2, our convention, one has to remember that formula 1 and formula 2. That's all. So when delta S and delta P are given, you have to find out the corresponding delta 1 and the corresponding delta 2. And then write the formula. So the formula is the following to calculate the order. So this is the simplest formula. So the order n is in the numerator minus 10 log to the base 10 delta 1 delta 2 minus, actually it is 14 point something. I simplified. Anyway, there is a lot of uncertainty, so you could use round numbers and keep your life simple. So I wrote this 15 in the numerator and plus 1. This is also not very important. This one is also not very important. If one second, if this whole thing comes out as 300 or 400 or 500, then 400 plus 1 or 400 minus 1 is not a problem. So this 1 is also not a problem. You can either add or neglect it, and divided by 14 times delta, and the used quantity delta, where delta in our notation is omega s minus omega p by twice pi. What is omega s? Omega s is the stop band edge, and omega p is pass band edge frequency. Pass band edge. So in other words, what they used as is the actual frequency difference, that is the bandwidth. Okay, so we will not go into this. Let me say this is formula number 3 and this is 4. We will not go into this 3 and 4. Okay, this 3 and 4 is a gross estimation. Once you get this estimation, you can go ahead and designing and do the designing, but you must find out the actual response and see whether it satisfies or not. So that one has to verify. So like this the FIR design starts, and this is a formula for the case of low pass FIR filter design, and generally this is going to be a small quantity, because the pass band tolerance and stop band tolerance, if you multiply and take log, then it's going to be a small quantity. That is why we put this negative sign here. There is a minus sign, and delta in our terminology is omega s minus omega p divided by 2 pi. Obviously for high pass filter, see this is for the low pass filter. Obviously for high pass filter it is the same formula, except that the delta is going to be omega p minus omega s divided by 2 pi. This is the only minor change for high pass filter. So what the formula transforms into in the case of band pass and band stop, we will discuss a little later. Okay, so that's all about the introduction to FIR filter design method, FIR filter design. So in the next lecture, we will see how to design the FIR filter using windowing method. Okay, filter design by windowing method, and followed by that we will see the frequency sampling method. So in the next lecture is going to be a little big lecture where we will discuss a windowing method. So there are many windows. We will discuss one by one in the next lecture. So let me stop here. Thank you very much.